Welcome back to a wintry lecture. It's almost November, it's October, but you have a few things coming up before exam number 2, which is happening in a couple of weeks, I think, actually, is exam number 2. And before that, you have homework 5 and homework 6. Homework 5 is dealing still with eigenvalues and eigenvectors. Homework 6 is getting into the inner product material of Chapter 6. And today I'm entitling, normally I don't give the lecture a title, but today's lecture is the Orthogonalization lecture. And I just like saying that, not that I can say it, but it's a mouthful. And we are talking a lot about orthogonal, orthonormal, and how we can play with that or use that, and it's a really powerful tool, and I want you to sort of take that away from today's material. We'll structure this orthogonalization lecture as outlined in the goals. We'll first look at orthonormal expansion of vectors, then we will see how can we build a set of orthonormal vectors, and this is not just restricted to these tall, thin items that have numbers in them. You can also think in terms of polynomials or other kinds of vector quantities, and you can apply the Gram-Schmidt orthogonalization process to those. We will simply state some corollaries, but those corollaries are really pretty cleanly understood from the previous material that we've talked about, but it's nice to just identify those corollaries as far as what they say. Then we will talk about orthogonal projections, or maybe a U-perp. We'll call it just a perp for perpendicular. If we have a subset U or a subspace U, and now we have to be clear on what we're talking about. It does mean two different things. But if we had a subspace U, we could talk about U-perp, which will be the orthogonal subspace from that one, and then we can actually create these direct sum decompositions of vector spaces with a U and a U-perp. And we'll also talk, I believe, about this, we'll get that far, with this projection operator, meaning how do we project on to a subspace. Maybe we're living on a subspace, and that will now lead us immediately into or directly into optimization problems. We might have a vector, and now we're trying to rewrite that or represent that vector, and we're restricted to only playing in a subspace U. We want to find the closest vector in U to the vector that we're given. And we want to go basically orthogonally from that vector U to get there. Let's now just recap what we have already talked about, and that is these orthonormal lists. And this was proposition 615, which says if we're given a list of vectors, E1 through E sub m being Michigan in size, and m may not be the same as the dimension of our vector space V. The vector space V may be of dimension 10, and m might be 5. So don't read into this that m is always the size of our vector space. But if we now combine this orthonormal list of vectors with scalars in our field, and we're combining those with A1, A2, where those subscripts are consistent with the orthonormal vector subscript, then the square of that norm can be found or is equal to just taking the absolute value of those, or the magnitude of those scalars, and squaring it, and then summing those squared magnitudes. And that's for all A1 through A sub n. And that's what that upside down A, if you thought I started lecturing upside down or right side up, that just means for all if I haven't already used that. That was proposition 615, and this is actually a very powerful concept or idea. Then we talked about corollary 616, which said that every orthonormal list of vectors is in fact linearly independent, and we showed that the reason that was the case is because we had that sum of magnitude squared equaling 0, and the only way for that to equal 0 is for all of those scalars to be 0. And we know that if all the scalars are 0 for a given list of vectors, that implies that that list of vectors is linearly independent. Then once we have an orthonormal basis, or we can find an orthonormal basis, or we can create an orthonormal basis, if we have an orthonormal list in V, and that list of vectors also spans V, then that is an orthonormal basis on that vector space V. And it's nice to be able to have access to or be playing with an orthonormal basis on a particular vector space. Any orthonormal list in a vector space of length dimension V forms an orthonormal basis. If you give me a list and you say, oh, this is an orthonormal list, what does an orthonormal list of vectors mean? They're pairwise orthogonal, aren't they? So you know that I'm now giving you a list that's pairwise orthogonal, and now I'm telling you a little bit more. I'm telling you that I'm giving you a number of those, and that number of those is actually equal to the length of the dimension of the vector space. And we can make this claim or this statement because of these two basically black sentences underneath that blue statement. We know from corollary 616 that you give me an orthonormal list, that list is linearly independent, those list of vectors. And now if you tell me that that list of vectors has the number of vectors in it is the size of the dimension of our vector space, then I know that because I now have linearly independent vectors that fill up the entire space, that's going to span the space, and that forms a basis. And that's the reason we can say any orthonormal list of dimension or of length dimension V forms an orthonormal basis. And the nice thing about having a basis that's orthonormal is now we can decompose any vector in our vector space in terms of this orthonormal basis. Just like any other basis that we have, we can write a vector in terms of that basis, but now these orthonormal bases enjoy a few more special properties, and one of those is that earlier result that we had, which was proposition 615, relative to what's the norm squared, or how could we compute, or how could we create the norm squared. Now let's slow down and start working through some of these new concepts based on what we already know. What we already know is this proposition 615, which allows us to compute the norm squared of any vector that we're building out of an orthonormal list. We know that those vectors are linearly independent, and we now know how many it's going to take of those vectors to create a basis. So Theorem 617 in the second edition says the following. If we have this list, E sub 1, E sub 2 through E sub m, and now I am basically saying that m is the right length, little m. If this list is an orthonormal basis, So that's maybe where you could get confused. Maybe I should have subscripted that with n. Maybe I will, but then I'll probably forget. But let's just distinguish that from what we've said before. Now n is the dimension of our vectors, or we have as many vectors that are orthonormal as the dimension of our vector space. If this list is an orthonormal basis, on a vector space V, then we can make the following two statements. First, we can say that any vector V can be rewritten or expressed as the inner product of that vector with the first orthonormal basis vector E1, scaling E1. Remember our inner product that takes two vectors and creates a scalar. That angled bracket is just a scalar now, and it's scaling the first vector E1. Then we can take V inner product with E2 and scale E2 and do that for all of these vectors in our orthonormal basis down to V inner product with E sub n and scaling E sub n. That's one of the statements that we can generate. And there is our decomposition of any vector in our vector space in terms of this set of basis vectors, E1 through E sub n. And the second part now follows really from the previous proposition, proposition 615. We can take those scalars and find their magnitude or their absolute value and square those and add those up, and that will equal the norm of V squared. And that's true for every vector in our given vector space V. That's the theorem, and that's a very powerful theorem. Let's now prove that, or just go through maybe the proof of the first. I'm going to sort of say that second statement is a direct result of what we already know from proposition 615. But here's our proof. Suppose that we now write the general expression for V, where V is now some scalar times E1, and the scalar we'll call A1, plus A sub 2 E2 plus A sub n E sub n. And we know that's true, or can be done, because we know these E's are are a basis in our vector space V. So we can find scalars A1 through A sub n to make this true. Now what we want to show, really, is that those particular scalars, all of those, are in fact these inner products, V with E sub L. That's what we want to show. And then we will have concluded the first part of those two statements in that previous theorem, in Theorem 617. Now to show that, let's start with the first one. Suppose that we form the inner product of this arbitrary vector V with the first orthonormal basis E1. We now are taking V with E1, and remember we've written V as A1 E1 plus A sub 2 E sub 2, etc. to A sub n E sub n, and we're inner producting that with E1. What do you think we're going to do next? Now that we have a sum in the first slot, what property of the inner product are we going to invoke to help us create the next line of this proof? What's the property of our inner product that we're going to use? We're playing with some terms that are added in the first slot. Additivity of the first slot. That's what we want to play with now, or use, so that now we have A1, E1 inner product with E1 plus A sub 2, E sub 2 inner product with E1 all the way down to A sub n, E sub n inner product with E1. And you probably don't know what that means, but this means that we have problems when it starts doing this, and I was afraid that that might actually happen. So let's see if we can come back and continue and not be rudely interrupted again, but I should have known better than I maybe know what happened prior to class during today that might have caused that, but we'll see. I don't want to replicate that process. What are we doing now, or what can we do now with this row of expressions of sums of inner products on the right? Relative to now, what do we have in the first slot when we really want to be finding the inner product of these orthonormal basis vectors? What do we know about homogeneity of the... So we can say that we can now invoke homogeneity of the first slot. So that A1 now comes out, and we have E1 inner product with E1. We have A sub 2 inner product, or scaling E sub 2 inner product with E1. A sub n, E sub n, E sub 1. Now we can use what we know about these orthonormal basis vectors. What's the inner product of E1 with itself? Pardon? Are you saying 1? These are normalized, right, to have length of 1, so E1 with itself is 1. What about E2 and E1? This is an orthonormal list, which says that they're pairwise orthogonal. That better be 0 by definition, and all of these are 0 after the one that is the same vector inner product with itself, which now says that that left-hand side is just A1 plus 0 plus 0, which is just A1, and that's really what we were setting out to show. You could now continue to do this. We won't. We'll just say repeat. But I think you see what you could do. You could do this for all n of those orthonormal basis. So now we have basis vectors. Repeat for all other vectors in the basis, which really shows that the inner product of V with E sub L returns what? What did V with E sub 1 return? a sub 1. So this is going to return a sub L. Or we can now just say, thus, we have V with E1 giving us A1. V with E2 gives us A2, and so on. V with E sub n gives us A sub n. And that now says that we can express V as A1, which is equivalently expressed as V inner product with E1, scaling E1, plus V inner product with E2, that's A sub 2, times E sub 2, plus V E sub n times E sub n. And that's the proof then of the first statement in that two-statement theorem. And just for completeness, I'll just write this down. The second half of that theorem, second half of theorem 617, which was just this second line, the norm of V squared is this sum of magnitudes of inner products squared. The second half of theorem 617 follows from proposition 615, and that's basically saying, or we're using, V squared is just A1 squared plus A sub 2 squared all the way to A sub n squared. This theorem is a way to decompose a vector into a sum of weighted basis vectors. And you can actually now go back and maybe better appreciate that now you have another way of sort of understanding this concept of the Fourier series. If you recall what computing, let's say, the nth coefficient in the Fourier series might look like, let's say this is the complex exponential Fourier series, we now are taking the period of that waveform, let's say f of t, and we're calling that capital T. We integrate over one period, but now we take the inner product of our function, f of t, with these basis vectors, e to the minus j n omega naught t naught, where that expression is really just an inner product. This piece right there is, if you index or you keep sequencing through the little n's, that would be our orthonormal basis. This is just one of those basis vectors. And this entire piece right here is our inner product, where all we're saying is that, recall that the Fourier series of, let's say, a function f of t is c1 e to the j omega naught t plus c sub 2 e to the j 2 omega naught 2, etc., for all of those c's. And now that's consistent with what we just derived in that earlier theorem, theorem 617, where we had an orthonormal decomposition of a vector in our vector space. We've now gone from finite dimensional, now we have a Fourier series expansion. I hope now that you see that these orthonormal bases are very useful. But now you're saying, okay, how do we build this orthonormal basis? If somebody just gives me a vector space, or if they give me some, maybe they give me a basis, how do I create an orthonormal basis from just a basis of this vector space? But how do we go about finding these orthonormal bases? Obviously, I wouldn't ask that question if I didn't have an answer. And what we're going to be using now is the Gram-Schmidt orthogonalization, which is one of the reasons why I called this the orthogonalization lecture. We're dealing a lot with this concept of vectors being orthogonal. And this is then, let's say, I don't know if it's a proposition or a theorem. It's probably a theorem in the second edition, 620. If V1, V2, he's stuck on V sub m. Well, I'll just go back to the book's notation, I think. V1 through V sub m. Let's say that this is a linearly independent list of vectors in our vector space V. Then there exists an orthonormal list E1, E2, E sub m with the span of, let's say, V1, V2 up to, let's say, V sub L is equal to the span of E1, E2, E sub L, where L, this is true for all L up to little m. For L equal to 1, 2, on up to little m. You give me a linearly independent list of vectors, and now with this proof that we're going to walk through, it's a proof by construction, we will build up an orthonormal list, E1, E2, E sub m. We'll see how to build these orthonormal lists by proving or by construction in this proof. First, let's let V1, V2 up to V sub m be a linearly independent list in V. And now you might actually underline that A. This is a linearly independent list. Is it the only linearly independent list that we could find in a vector space V? Can you have multiple lists of linearly independent vectors in a given vector space? If I give you R2, can you only come up with one list of linearly independent vectors in R2 that could even be a basis? I'm not even saying these are yet a basis. I'm just saying, give me a list. if you said R2, can you come up with more than one list that's linearly independent for vectors? Yes, right? You could have an X and Y. That would be a list, and it's a basis, the X-axis and the Y-axis. You could come up with the diagonal, XY and Y, and that would be a basis, and they're linearly independent. That's all we're saying right here. We have a linearly independent list in the vector space V. That's the only assumption that we're making, and we can make that. Where little m could be 1 if we wanted. We can say, oh, I'm just going to pick the first one and then see if I can keep building this up and up. Now to show this, let's start with, we're going to prove this by induction. Because right now we want to show that this is true for L equal to 1, 2, up to m. This is sort of begging us to maybe apply the proof by induction technique. And if that's the case, then we have to start with showing that it's true for a base case. And in this case, let's let our base case be L equal 1. In the base case, in this inductive proof, we are going to let E sub 1 be V1 over the norm of V1. What do we know about the span of E1 relative to the span of V1? Can we relate these at all? Do you see that these are the same? V1 could have been, let's say, any vector on the x-axis. Now we are just normalizing that vector to have what kind of a length? We've now taken V1 and we've normalized it by the norm of that vector so that now E1 has length 1, but they are spanning the same direction. We now have E1 as the span of V1, and E1 by definition has a norm of 1. And that then verifies the base case. We need, for the base case, we would need to show that this is true, this span relationship for L equal 1, and we just did. The span of V1 is equal to the span of E1. In an inductive proof, we now can assume that it's true for all the remaining, let's say, L's up to, let's say, J, or some M in this case. Continue by induction. Which means that we can now assume that J is greater than 1, and E1, E2, up to E to the J minus 1 has been found so that this span relationship, the span of V1, V2, up to V sub L minus 1, or J minus 1, I need to keep my indices consistent, is equal to the span of E1, E2, E sub J minus 1. And that's the inductive step. Now let's build up the next vector. Let's now let, and we're going to build this next vector E sub j in 2 pieces. First, let's let W sub j be V sub j minus V sub j inner product with E1, scaling E1. And what's that doing? What's this first step doing? What's that inner product actually doing with V sub j and E1? It's the inner product of Vj with E1. What's that telling us? What if Vj was in a direction orthogonal to E1? What would that inner product do? It would go to 0. What if they were aligned? What if E1 was in the same direction as V sub j? Then it would be a very strong number, wouldn't it? They would be very strongly correlated. This is sort of giving us this overlap or correlation between V sub j and E sub 1. But we know by definition that V sub j is not completely aligned with E1 because the V's that we started with were linearly independent. So we know that this is not going, this right-hand side is not equal to 0 right now, by definition. Vj is linearly independent. But we can remove the component of Vj that's in the direction of E1. We can also remove the component of Vj in the direction of E sub 2. And we just keep removing the pieces of V sub j that are in the direction of these previous orthonormal basis vectors, E1, E2, or this list of vectors. V sub j, E, and how far were we going? J minus 1, up scaling E to the j minus 1. That's our first step. And let's just state what we've done in words. We now have subtract, or this subtracts off all parts of V sub j that are along the E sub L's. We're now removing the component of V sub j in the direction of all of these E sub L's. And we know that we aren't going to end up with 0 on the right because we assumed that all of these V's were linearly independent. Something must be left, or something must remain, since all of the V sub i's that we started with are linearly independent. And what's left over, that's the W sub j. What's left over from this right-hand side from taking away all of these pieces in those directions is actually perpendicular to every one of those E's so far that we've removed. The remainder, and that's the W sub j, the remainder is perpendicular to all E sub i's that we've removed. E1, E2, E sub j minus 1. Now we have W sub j created, which has a little piece or a big piece, but it's orthogonal to all of the E's so far that we have used. What can we say about the length or the norm of W sub j? Do we know anything about the length of W sub j? It's going to be, well, it's related to Vj, isn't it? But what can we say about the length of V sub j? Is it It's norm 1 is the norm of V. No, we just said Vj is a linearly independent vector. Now we know that what's remaining is not guaranteed to have a length of 1. That's our second step. Let's normalize W sub j so that it does have a length of 1, and then we can call that resulting vector our E. So this is the second step in this process. Let's say then, let's let or build E sub j is equal to W sub j over the norm of W sub j. What can we say about the direction of EJ and W sub j? They're the same direction, aren't they? They're just scaled versions of one another. The norm of Wj is just a scalar, and we're dividing by it, and that's actually the length of W sub j. So E sub j is the same direction as W sub j, and in fact it's perpendicular to other E sub l's And what's the norm of E sub j? We've now normalized it to be 1, since we're dividing W sub j by its norm and calling that E sub j. If we now combine this second step 2 with that step 1, now we've built what we need. 1 and 2 together imply that V sub j is now in the span of E1, E2, E sub j. Or therefore the span of V1, V2, up to V sub j is contained in the span of E1, E2, E sub j. And we know that both lists are linearly independent. We also know that the lists are the same length, or we have the same number of vectors in each list. Both lists have length j, and that says then that the subspaces that are spanned by each of those sets or lists of vectors is the same. And therefore the span of V1, V2, V sub j is in fact equal to the span of E1, E2, E sub j. this theorem, which was what, 617, oh no, 620, this Gram-Schmidt orthogonalization is really powerful. This theorem is pretty powerful, and one of the nice things is that we proved it via a proof by construction. So now we can just construct this proof and find a list of orthonormal vectors whenever we want. And its proof was by construction. Which says that we not only know that it's possible to have an orthonormal basis, but we can actually build it. We not only know that it's possible to have this basis of orthonormal vectors, but we know how to construct the orthonormal basis. Now, we could almost stop the class at this point. I mean the class for the whole semester. This is a big thing. But we're not. Now we're going to start learning how to use this to our advantage in optimization. And before we do that, let's just look at some results that we can take away from this that are useful. A number of useful results are now possible. And I will just state those, and I will refer you to the textbook for the details. Right now, we just sort of want to know what these results say. First is corollary 624, and that says, and this is coming from the second edition, every FDIPS, what in the world does that mean? Finite dimensional inner product space, every finite dimensional inner product space. And what's an inner product space? A vector space with an inner product. So every finite dimensional vector space with an inner product has an orthonormal basis. Which means if you have a finite dimensional vector space and you can define an inner product on that vector space, now you can have an orthonormal basis. And what can we do with an orthonormal basis? We can decompose any vector in that vector space with this combination of orthonormal basis vectors. Corollary 625. Every orthonormal list in a vector space V can be extended to an orthonormal basis on that vector space V. It says every orthonormal list. So your orthonormal list could just be one vector. And maybe you have a vector space that's 20 in size. this corollary says, oh, I can extend that one vector and create an orthonormal basis that is a basis for a 20-dimensional vector space. Corollary 627. Given T, an element of script L of V, oh boy, what's that? What does that mean? That's now an operator, isn't it? And it's operating on a vector space V, and it's a linear operator, which means it's mapping from the vector space back into itself. So we're given this operator T, it's a linear operator. If this operator, linear operator T, has an upper triangular UT representation, with respect to some basis then that linear operator T actually has an upper triangular representation with respect to an orthonormal basis on V. Where this orthonormal basis is really just the Gram-Schmidt orthogonalization process on the original basis. Which means if you have an upper triangular operator on some basis, then you can simply perform the Gram-Schmidt orthogonalization process on that original basis and obtain now an orthonormal basis on this vector space to give you an upper triangular representation of that operator. Corollary 628. This one also has another name associated with it, and this is Schur's theorem. Maybe the next test will just be a matching test. Match the theorem with the author. No, probably not. Let's learn how to apply these famous results. So now let's say we're given V, a F, D, C, I, P, S. Now you had the last one right, and all I've done is introduced one more consonant into this. This is just now a finite dimensional complex inner product space. Given V, a finite dimensional complex inner product space, and an operator on T, and given a linear operator T on that vector space, then in fact this operator T has an upper triangular representation with respect to some orthonormal basis. Now we can start talking about, those are sort of our results or facts. We said after that we would start talking about projection. And the type of projection we are going to be talking about is orthogonal projection. Here, let's say that we're given U, a subset of V. Now, I'm making a big deal of this, or a big distinction. This is a subset of a vector space. It's not a subspace. A subset. Given U, a subset of V. Now, we can define, so here you could just think of the integers on the x-axis, and that would be a subset of, let's say, the R2 plane. We can now define the orthogonal complement of that subset U. And we are going to give that a particular name and notation. We're going to call that orthogonal complement U perp. U with a superscript with a perpendicular symbol, called U perp, and that's really just a shorthand for U perpendicular. And U perp is the set of all vectors in our underlying vector space V that are orthogonal to all vectors in our subset U. You give me a subset, U, and now U perp are all of the vectors in V that are orthogonal to those vectors in the subset. The notation that we will use is then U perp is this set of vectors V in our underlying vector space, capital V, such that the inner product of V and U is what? This is now U perp. This is the set of U perp, and we want this now to satisfy really what we just said in that black couple of lines above this blue. We want all the vectors in our vector space, which we're now calling little v, to be orthogonal to the vectors in U, and little u is in capital U, which says, what do we know about the inner product of V and U? By definition, we want V to be orthogonal to all of the vectors in our subset U, so we want this inner product to be 0, and we want that to be true for all little u in our subset capital U. Now, this is where we start getting mathy, maybe, meaning with respect to the way this next statement is made. It should be obvious. And anytime you hear that, that's where you need to kind of stand up and start saying, whoa, obvious. Okay, yeah, right. So it should be obvious that U perp is a subspace even when U, let me say, could be just a subset. U can, at some point, we may be referring to U as a subspace, and then U perp will be a subspace. But here, the book is saying it should be obvious that U perp is a subspace, even when U maybe just be a subset. So let me just say that here. U is a subset not necessarily a subspace. Now, this may get just about as wordy, but let me see if I can write down a sentence to try to justify that. Remember, we have an underlying vector space, capital V, and we have a subspace or a subset on that vector space that we're calling U. U perp are all the vectors in capital V in our vector space that are orthogonal to that subset, or all the vectors in the subset U. Meaning, the only part of our vector space V that is not, let's say, in U perp are those vectors that are perpendicular to all vectors in U perp. That sentence is really just U. The only part of our vector space that isn't in U perp are those vectors that are perpendicular to all vectors in U perp. Now, if that's the case, if we have a bunch of vectors that are orthogonal to U perp, what happens if we start adding things in U perp? We still can't get to that set that's in that first sentence. We can't get to U, can't get to them, i.e. U, or the vectors V minus U perp, that's U, through or addition or scalar multiplication of vectors in U perp. So if you start adding or combining vectors in U perp, and they're only in U perp, and all the vectors in V that are not in U perp are in U, can we ever get to U by combining vectors in U perp? So that tells us that we remain in U perp if we start in U perp. Now we're back in Vegas. If we have vectors in U perp and we combine those in any way we want, we are going to stay in U perp. That's really what this is saying. And if that's the case, what's that tell us about a particular property of U perp? U perp is now closed under arbitrary linear combinations. What else do we know? If I now said, oh, the zero vector is perpendicular to everything, that means the zero vector is perpendicular to everything in our subset U, and everything that's perpendicular to our subset U belongs where? All vectors that are orthogonal to U belong to U perp. So 0 is in U perp. And now that we have 0 in U perp, and U perp is closed under arbitrary linear combinations, which means that we have homogeneity and linearity, then we have a subspace. And that's what we were trying to justify, that U perp can be a subspace even though U could be a subset. So 0 is perpendicular to everything. So 0 vector, or 0 element, is in U perp. And that's what we need for U perp to be a subspace. This next result, though, sort of extends this idea. Suppose that now we start with U not being just a subset, but suppose U is in fact a subspace. Then, in fact, it's possible to create our entire vector space V by taking two vectors. We can now write any vector in V in terms of two components. One component in U and the other component in U perp. And that's this direct sum decomposition of these vector spaces, or I'm sorry, of these subspaces to create the vector space V. We can also say that we have corollary 633, which says that so now remember, we're distinguishing, now we're saying that U is a subspace. In corollary 633, we're also making that claim. If U is a subspace, not a subset, if U is a subspace, then what is U perp perp? What's U perp? It's a subspace. How is it related to U? How is U perp related to U? How are the vectors in U perp related to vectors in U? If you form the inner product, what would happen? You give me a vector in U, and somebody gives me a vector in U perp, and we form the inner product of those two vectors, what are you going to have? They're orthogonal. It's going to be 0, isn't it? So now we're saying, oh, I now am in U perp, but you're telling me to find the pieces that are orthogonal to that. Now we're just back to where we started in U, aren't we? The perp of U perp is just U. Let's look at some examples of these results before we start trying to have our heads spin too much. Suppose now that we say that our vector space is two-dimensional. Now you just have to think about the desktop in front of you. Have this two-dimensional real space. And now let's let this U be the x-axis. Is that a subset or a subspace? If I'm in R2 and I say, oh, I'm going to give you the x-axis, is that a subset or a subspace? It's a subset, but it's also a subspace, isn't it? Because you can stay in U if you start in U, right? And you can get anywhere you want in U from anywhere else in U. So it's closed under addition, and it contains the zero vector. So this is a subspace of R2. What is U perp? What is orthogonal to the x-axis? The y-axis. In R2, the y-axis and the x-axis are orthogonal, and now it should be clear that we can do a direct sum decomposition of U and U perp. That's just the x-axis and the y-axis. You give me a vector, and I can give you a unique representation of that vector from a vector combination of x and y. X belongs to U, and y belongs to U perp. What else do we know about that? If I now said, oh, what if I take the orthogonal or the perpendicular of y? That's what I'm saying on the right. U perp is y. Now I want the perp of y. That's back to x, isn't it? So now you can continue to do this in 3 dimensions if you want. You can keep going in this, but now you might have planes instead of lines. So that now if you said U, if we were starting with V of R3, it's just easier to visualize in 2. But now if V was R3 and U was the x-axis, what would be U perp? It's the YZ plane, isn't it? That's the U perp. Now let's look at a different example. Suppose now that we say V is still R2, so we can complicate this even in R2, but now let's let U be the vector 3, 0. Is that a subspace or a subset? What we have to realize now is that is U equal to the span of 3, 0? What's the span of 3, 0 mean? That means you can take any linear combination of 3, 0, and that's the span. Is the point or the vector 3, 0 equal to the span of 3, 0? It's a fine distinction, but it's not the same. We're just at a point if we say 3, 0. But the span of 3, 0 gives us the entire x-axis. Is it clear the distinction? In this case, U is a subset of R2. And because of that, Now V cannot be built up from U plus U perp. What is U perp? Should say what is U perp. What's orthogonal? What are all the vectors in V, in R2, that are orthogonal to 3, 0? That's again the y-axis, isn't it? And that is a subspace. But is it clear that V cannot be built from the point 3, 0 and the y-axis? Likewise, we can't say now that U perp is not U. So now U perp needs to be all the vectors that are orthogonal to the subset U, and that can be the y-axis. That's the y-axis. What gives you this translation in the, let's say, horizontal is the component in the x direction, but we don't have a component in the x direction with the y-axis. But now, what's the perp of the y-axis? That's the x-axis, and that's not U. Is that clear? So we'll have to pick up at this point next time, but we want to start thinking about how do we project onto subspaces U from a larger vector space V. And we'll use this orthogonal decomposition concept.